What's up, guys? This is Jahangir from Medporium, and today we're going to be diving into organic chemistry 2. So yeah, I'm not as excited as you are in terms of taking another set of organic chemistry, but I gotta be honest, it's not that difficult compared to organic chemistry 1. Because, I mean, if you went through OChem 1, you already know the basics of, molecules, how they interact, those functional groups. So just building off of that knowledge, it's actually pretty easy to understand organic chemistry 2. Maybe not easy, but you know what I mean, just a little bit easier. So today we're going to be talking about mass spectrometry. So mass spectrometry is a sort of method that many scientists use, and we use this method, here let me change my cursor over here, we use this method to measure mass and the molecular weight of a molecule. So over here I have a picture of what mass spectrometry looks like, just got it off the internet. So over here, this is pretty much like the starting point of everything. So this is where we inject a sample of like some random organic compound. And what happens is there's three basic parts to this sort of machinery. The first one is going to be, let me change this real quick. First one is going to be ionization. So our first part is going to be that ionization source. The second part is going to be the mass analyzer. And this is where our ions will be separated from their mass to charge ratio. So it would be somewhere over here where that magnet would basically separate our particles by their mass to charge ratio. And then we're going to have our detector. So right at the end of our mass spectrometry, we're going to have that detector. So detector. And our detector is basically going to separate those ions as we observe them and count them so we can see the relative abundance and that specific mass to charge ratio, that M to Z. I'll write that real quickly. So it's M to Z, and M-Z is indicating, is just a symbol to show that mass to charge ratio. Throughout this entire video, we're mostly going to be talking about electron impact and that magnetic sector. So that's basically when we're going to have those high energy electrons that strike our organic molecule, and that's when they're going to divide to cation radicals. So I'm going to write that down real quick. So this is basically what it's going to look like. So this RH over here, just put it as a random thing. This would be representing our organic compound. So organic compound, that R is just an R group, like whatever carbon group we have, either methyl and ethyl, anything like that. So that is our organic compound. What happens is that there's going to be a high energy electron that strikes our organic molecule and pretty much dislodges its valence electron. Now, we're going to go back to some basic stuff in chemistry, which is ionization energy. Now, if you guys remember about ionization energy, you know that it's easier to take those valence electrons compared to those core electrons, because those core electrons are so close to the nucleus that the nucleus, those protons, are pulling those electrons. So it's really hard to take those electrons away. That's why we could take out those valence electrons, because they have a low ionization energy, which makes it much more easy to pull out. So when we're striking our organic molecule with these high energy electrons, we are going to be dislodging that valence electron. So over here, this electron right here, that is our valence electron. What happens is we are going to create a cation radical. The cation part comes from that plus charge we see over here, and the radical comes from that odd number of electrons, which we are showing by that dot. And what happens is that these cation radicals are going to fragment into neutral and positively charged fragments. So I'm just going to write this over here. I'll just represent our cation radical as Cr. So Cr will fragment. And when they fragment, we're going to create these fragmented ions. Now, the key thing to note is that these cation radicals can fragment into neutral or positively charged fragments. Now, you have to know this one key thing about mass spectrometry, and it is that the positively charged fragments will always pretty much stick to the wall. We only care about those positively charged fragments because these are the ones that are going to be accelerated through the entire mass spectrometry. And when we look at that mass spectrometry graph, looking at the relative abundance and the mass charge ratio, those are going to be only from the positively charged fragments. Neutrally charged fragments will just be deflected from the pathway. So overall, neutral fragments we don't care about. If we see any neutral fragments, we're basically going to forget about those. We only care about those positively charged fragments. So it would be something like if we had CH3, CH2 plus, or if we had something like CH3, CH2 with a radical and plus. Doesn't matter if there's a radical, as long as we are positively charged, this fragment over here is going to pass that mass spectrometry. Now, a key thing to note is that we don't really know what specific bond loses electrons. So you're going to see that when we're writing these molecular ions, we're going to write them in brackets. So for example, if we had, let's say, let me move down over here. Let's say we had something like this, CH3, CH, and that's bonded over here to H3, and we have CH, oh, that's too far away, CH2, CH3, and we have those brackets. We have to put those brackets because we don't know which bond will lose that electron. So we're going to have our radical over here with a plus, and our fragments, and when we look at how it's going to fragment, I'll show you guys a graph of mass spectrometry, but just to show you where that fragmentation occurs, where we could say that that could occur, it could occur right here at this bond. So what would happen is the fragments that are created are, we have CH3, CH bonded to that methyl, and we have CH2, CH3, so we have a plus over here, we have that radical over here, and this over here, our starting molecule is going to have a mass to charge ratio of 72, and this one is going to have 43, and this one is going to have a 29. So where I got those numbers from are just the molecular weight of each of these. So since we have 1, 2, 3, we have 3 carbons. So 3 times 12 is 36. And then we have 7. So 36 plus 7, that gets you 43. So now this is the biggest thing to note, is that our fragments are going to add up to our initial molecule, that molecular weight that we had. When our starting this cation radical over here, that molecular weight is going to equal the fragments that are created. If that didn't make any sense, don't worry, because we have a practice problem right here. So this compound, the starting compound that we have over here is going to be C8H18. So if this is C8H18, one of the isomers that we could draw out is a regular hexane. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So we could do that. We could do a bunch of other isomers, but for now I'm just going to go off of this diagram, looking at just hexane, because this essentially is just hexane. If that didn't make sense, don't worry, because I have a mass spectrometry graph over here, and I'm basically going to dive into how to sort of read this. So now this tall peak right here, you can see it has the highest relative abundance, and this is known as our base peak. And a base peak, if you have a really high base peak, that means this is the most abundant ion. Now over here, this sort of spike over here, this is about 114. So I'm just going to change my colors real quick. So this over here is 114 mass to charge ratio. This over here is going to be known as our molecular ion. So molecular ion, or it's also denoted as just M. And molecular ion is basically going to be the molar mass of our compound. So that's just going to be 114. And you could also check, you could also do the math. If we have 8 carbons, 8 times 12 plus 18 will get you to 114. Now, there are different isomers we could draw with this octane. Like we could just draw regular octane. We could draw like 4 methyl heptane. We could draw a bunch of stuff, but for now, I'm just going to go off of a regular octane. So this is our regular octane. Now let's go through some of the peaks that we're looking at. And first off, let's start with this tall peak over here, our base peak. So if we're looking at this base peak right here, the base peak is about at 43. So we're gonna have our base peak being 43 mass to charge ratio. We're gonna have it be 43. Now, if we're looking at our octane over here, to find out which fragment is present, we have to understand that this is all just molecular weight. This is all just molar mass. So all we have to do is figure out how many carbons and how many hydrogens do we have to add in order to get to 43. So obviously you have to start off with a methyl. That's the end of the tail. So we have a CH3, and right now the number we're at is 12 plus 3, so that's 15. So we're at 15 right now. So let's say we add a CH2, because we're just looking at our octane. We're seeing how much of that octane can we break apart to get to that number 43. And that will be our fragment that is abundant. That is actually the most abundant ion that will be seen in our mass spectrometry, shown in our mass spectrometry. So we have 15 plus carbon is 12 plus 2, that's 14. So right now we are at 29. Now let's say we add another CH2. So if we add another CH2, that is going to be another 14. So that will be 29 plus 14, which is going to equal 43. So this fragment over here, and obviously we have to put a positive charge, because like we talked about, the only fragments that are shown in our mass spectrometry are always going to be positively charged. So if you're still kind of confused, think about it like this. We're looking at our mass spectrometry. First, we need to find our molecular ion. Our molecular ion is usually going to be at the end over here, and that's going to be represented as M. That is just our molecular weight. So that's all the molecular masses added up with that compound. Now, to find like for example, this base peak or any of these other peaks, we need to look at the mass to charge ratio and find how many carbons or hydrogens that we can add to get to that specific number. So over here, we had to add 3 carbons and we needed 7 hydrogens. So you also want to just draw your compound out and just look to see which fragments you could take off. So over here we had CH3, CH2, CH2. So we basically fragmented this molecule over here, this organic molecule, so that this fragment over here, and I'll draw it in terms of, organic chemistry, this fragment right here is going to be our most abundant ion in our mass spectrometry. Now, we can go through this process again. Let's say we wanted to look at this guy over here, this peak right here, which it looks like it's about 57. So 57 mass to charge ratio. All we have to do is think about, well, how can we get to that lucky number of 57? How can we get to that special 57? All we have to do is look at our isomer, look at our molecule, and see, what can I add? If I'm moving this way, I need to get to 57. The closest thing I have is another CH2. So if you add 43, because we're looking at this molecule over here, and we add another CH2, 43 plus 14 is going to get us to 57. So this guy right here, this peak right here, is going to represent this ion right here. So all you really have to do is just count how many carbons, like draw out your organic molecule, count how many carbons that you can get to this mass to charge ratio. And we'll just do one more, just for fun. So for this one over here, we're at 29 mass to charge ratio. So then all you have to ask yourself is, well, how many carbons and how many hydrogens going down my isomer do I need to get to 29? Well, all you really need is CH3, CH2. Obviously, we have to put that plus charge because only positively charged fragments can go through our mass spectrometry. They're only shown in our mass spectrometry. So we know that this is 29, and this is the fragment that will be seen when this is what our fragment looks like at 29 mass per charge ratio. So let's just say we have C5H12, but these are all constitutional isomers because they have different arrangements. They all have 5 carbons, 12 hydrogens, but their arrangement is different. So let's say we put all of these molecules into the mass spectrometry. And let's say, for example, we were looking at the peak of 57, so that mass to charge ratio of 57. Now, our molecular ion is going to be 72, and we'll just say 72. There's 72.15, but we'll just say 72 just to make it easier. So we have our molecular ion of 72, and we need to get to 57. The reason why I'm just saying the mass to charge ratio of 57 is because all of these are going to have a peak of 57, but their intensity is different because of the stability of that carbocation, that we're going to see. So all we have to do to get to 57 is just have 4 carbons and 9 hydrogens, because 4 times 12 plus 9 is going to get us to 57. So our magic number is going to be 57. Now, obviously, we have to put our cation radical. We're always going to start with cation radical, so that's why we put brackets. We don't know specifically which electron we'll be losing, so we just put those brackets, so the positive and the radical. And now if we're going to get to that C4H9 for this molecule over here, for that 2-dimethyl propane, we are going to need to lose that methyl. So when we do that, we're going to have our carbocation right there, and our CH3 is going to have an uneven amount of radicals, so it's going to take that extra electron. It's going to be a radical. So this over here is a tertiary carbocation. Now let's look at the other ones. Over here, we have to lose that CH3. So the only way we can lose the CH3 is at this carbon over here. So what happens is we are going to create a primary carbocation. Our radical of CH3 is right there. And over here in this one, we have to lose that CH3. Easiest one we can lose is on that secondary carbon right there. So we would lose that fragment, we lose that methyl. Methyl is going to have that radical, and as you can see, we have a tertiary, we have a primary, and we have a secondary carbocation. I'm just putting first, second, third just to indicate primary, secondary, and tertiary. But one thing you'll notice, and that we learned in Organic Chemistry 1, is that tertiary is going to be the most stable. It's going to be the most stable sort of carbocation that we can form. So remember, we have tertiary is going to be superior, then secondary, primary, and then we have our methyl. So all of these are going to have a peak at 57, but the most intense is going to be from that 2,2-dimethyl propane. Reason why is because this is the most stable form of that fragment that we can create. This is the most stable fragment that we can create out of all of the mass spectrometry. That's why this is going to be the most intense. It's going to be the base peak when we see that in that mass spectrometry. All right, and that concludes our introduction in mass spectrometry. So we basically talked about like what mass spectrometry even is and how it forms those cation radicals and those fragments. Later on, we're gonna have more videos diving into those isotopic peaks and more practice in that field of mass spectrometry, so we can actually look at those graphs and identify what exact molecule that is. But for now, as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.